I'm going to start off with the bad news. The bad news is we got delayed moving all this stuff into and missing some parts, so you're not going to get a really awesome visual. So you guys are going to get the video version. So hopefully a little bit afterwards we'll set this demo up someplace else, and we'll let you guys see some physical damage firsthand. So first with the bad news, and then the warning that we don't need. So the original warning was this will be a presentation on physical damage, and there was going to be loud bangs and stuff. But now you'll get video of loud bangs and stuff instead of actual loud bangs. So just briefly then. Lately, I've had a few comments that I've been doing lots of presentations on chemical processes and that type of stuff, and I've really been neglecting the actual power guys. And so this one actually is going to be mostly geared towards chemical and manufacturing systems. But if you like power type stuff, then over at the ICS Village later this weekend, then Shaw, Cullis, and Thuin will have a model of the West Coast power grid that you can sit down there and try and take out stations and try and destabilize the West Coast power grid. So that'll be really fun if you're actually into power and that. So Sergey Bratis talks a lot about exploitation, and he talks about software exploitation, and he says that software exploitation can be described as unexpected computation. You throw some stuff in there and it goes. So once you start studying physical damage, then cyber-physical exploitation can be described as unexpected physics. There's a process that's supposed to do something, and you, the attacker, are attempting to run over there, grab the process, and make it do something entirely different. Usually that doesn't happen out towards anybody else. So where we're falling in this presentation in kind of the stages of things. So for those of you that haven't seen any of my other presentations, so hacking process control systems generally falls down into stages. So first you have the access stage where you have to go hack into the process. So if you're sitting in your coffee shop over in France and you really hate some company somewhere, and you've got to actually hack in across it. So next, you've got to go through the discovery phase. That's where you grab all the screenshots, one-line diagrams, everything you can find on this place, and try to figure out how it's physically laid out. A plant is a series of pipes, valves, pumps, and you need to know that. Finally, we hit the control phase. So a process is actually a dynamic thing. So if you come over there and look at it, it's like, hoo-hoo, here's a boiler, and there's a burner under it. I'm just going to crank the burner all the way up, and I'm going to make the boiler explode, and all things will be bad. That usually isn't what happens. Usually when you crank up the boiler, the temperature happens, and all the pieces of this process are related in a physics relationship. So if you increase the temperature, you also increase the pressure, you may increase flows, etc. And that's going to cascade down through the process and set off alarms, shutdown routines are going to kick in, and all that type of stuff. So in this presentation, you're assumed to do all that. So then we're hitting the damage phase, which is mostly what this is about. And so back at Black Hat in 2008, I described damage in a bunch of different ways. Inertial attacks where you spin things, exclusion attacks, those types of things. But I haven't talked a lot about the mechanism of physical damage. And so we're going to be talking about that today. So this is pretty typical in my day. So I come over there and I hack across all the things. I get through all the microcontrollers and stick some firmware implants in and tell the people that hired me I have full control of the process. And they're like, okay, show me insert evil thing here. You know, if it may be I want you to try and make the screw come off the back of the boat, or I might want you to run one car into another car or something like that. So I say, okay, I have full damage, and they say, okay, show me this evil thing. I'm like, give me a couple of weeks. And they're like, I thought you had full control. And so the problem is Hollywood has conditioned us that once we get into a control, there's a big red button that says, mash the big red button, and things explode, and stuff goes everywhere. And so in reality, you've got to analyze the process and actually build your big red button. So there's a lot of attacks that are specific to the process. So in a vinyl acetate process that we study a lot, then it actually comes with a bunch of things that it says. It says the peak reactor temperature must remain below 200 degrees Celsius to prevent physical damage. And so that's something specific to the process. I just did one a little bit ago where they used some nasty acid, and the nasty acid gets above 40 degrees Celsius, then bad stuff happens. They say it's not actually an explosion, but it's close enough that nobody else would care. So every process has these specific attacks that can happen. And most of the time when you talk to engineers, we get what we call the salty cookie problem. So if you, there's an experiment that was done a number of years ago, actually in a cookie factory. And they went up to all the engineers and said, okay, if you can hack into this cookie factory and really do some damage, what are you going to do to this cookie factory? And almost all the engineers came up with the equivalent of salty cookies. They're like, oh yes, there's this recipe for the cookies, and we'll just add lots of salt to the cookie. And then the machine will put out salty cookies, and they'll be salty. And then they threw the hackers at it. The hackers went through and crashed all the PLCs, and the cookie dough set up in the pipes. And then they tried with a heavy water pressure to push the cookie dough out of the pipes, and then they tried chemically eating the cookie dough, and eventually they cut the pipes out and threw them away and put in new pipes. And so none of the engineers actually thought about this very simple mechanical attack, because engineers think about the hard problems for the specific process. So usually the guys that run the process are really bad at predicting what the hackers are going to do. So if you're hacking into a process, this is probably what you already have. So this is just the layout of a vinyl acetate process. So you've pulled all these back in your discovery phase, and you've figured out the layout of the process. But more than that, you probably have all this other stuff too. So you've got one-line diagrams that are running, so you know how things are hooked together. You've also done your dynamic manipulation, so you've watched disturbances propagate across it, so you know changes in this propagate across and cause ringing in these loops and that type of stuff. And probably you've already pulled back the ladder logic. You know how the ladder logic works, and you've done all your research on particular plants and look to see how these plants have historically failed in the past. So one place I always go to is like the National Chemical Safety Board. So you can go look up, okay, vinyl acetate plant, and then you pull up all the things about all the ways the vinyl acetate plant has actually gone horribly bad. And you've probably also done all of your dynamic research. So you need to know how everything is interrelated. So if you touch something and it propagates, it'll propagate to all the rest of the pieces of the process. And you need to know how all that works in order to get it done. And so Marina Crotophill is actually doing a presentation on how to construct this dynamic view of the process, so that if you come in and disturb it, then it wiggles, and you track the disturbances to all the places that it goes. So let's start with considering this process. So this is an HMI that I pulled off the internet years and years ago. People love publishing their stuff out on the internet. So this is obviously a heat exchanger loop of some sort. We have a tank full of acid and a tank full of basic detergent and some cooling water. And so those are probably there to neutralize the water as it's running through. And so we can go look at this and look at different things. So if we take acid and we put it into the pipe, and basic and we put it into the pipe, and an acid plus a base is going to make a salt plus a water and lots and lots of heat. So perhaps we could heat up this loop and push stuff through the heat exchanger. There's a bunch of stuff that we could do here that we could think about. And so I'm going to come back to this at the end of my presentation, and maybe people will have more ideas about what they could actually do. So this was going to be the my demo, and we'll just switch over and do this one as a video. So this is actually something most geeks can actually understand, which is a bootleg whiskey. So we have a hot tank. That's where you put all your mash, where you fermented all your alcohol. You heat it up with a control loop and get it all nice and hot, and then you transfer the alcohol vapors over into to the second tank, and then you cool that tank down, and you start condensing it. And then there's a pump in the bottom that you pump out your alcohol. So on this particular one, then I'm just going to exit this real quick and go into video mode instead of doing it live. So in this particular case, I was going to show a steam collapse where we put it in. So this is basically this experiment for the last set of unlucky barrels in my shop before I came here. So so in this case, what we're going to do is we're going to for the attack is we were going to heat up the steam in the tank, transfer it to the other tank, and then kick in the cooling loop. And then the pressure increases, and you can kind of see the barrel popping down. And then eventually the pressure in the barrel is going to get to negative enough that the barrel will actually crush, which would have made a really awesome demo on stage, but unfortunately we didn't get it there. So let's talk about the actual mechanisms of physical damage and how we'd go about this. So the first thing that you usually find is place-shifting chemical reactions. So one of the things that as the attacker, then you're the great god of all the pipes and valves and switchy things. And so chemical reactions are supposed to take place in things like this, great big pressure vessels that are all stamped and rated and that type of stuff. So a lot of the times these things have heating and cooling sleeves, but they also have all the defenses that the process control guys build into them. They have pressure relief valves in case you overpressure them. They have catch basins sitting out below them in case stuff boils out over the top and runs into the bottom. They have burst discs that will relieve the pressure for sudden pressures, and they have ratings that says we've tested this thing out to so much pressure and it took it. So where and when something happens is almost completely under attacker control. So if we have a tank and a bunch of valves and switches, valves and pipes, then when those valves are open and closed are almost always the things that once you hack into it, you have control of. So you can heat stuff up and move it around. So this is a pretty common diagram where we have a couple of different tanks in the holding pond, and they're pumped through a common pipe up into the reaction vessel. So in this case, we can just reverse that and pump things back into the holding tanks, etc. We can move the chemical reaction of unreacted stuff up into the cracking column off to the left if we don't heat the tank up to its reaction temperature. So the problem with place-shifting chemical reactions is the heat. So if you take a bunch of unreacted chemicals out of a vessel and then move it into the piping structure, most of the time it's not going to start reacting violently. So most reactions have an activation temperature, and so as the attacker, you have to go find an alternate method of heating it up. To move it across. So we'll cover that a little bit more later. So the next mechanism of physical damage I'm going to talk about is when water doesn't stop suddenly. So if you have a bunch of stuff, if you ever have a house that you go and you turn the faucet off, and then off from some other part of the house you hear a thunk. That's actually a water hammer. So all the water when you kick off the faucet is backing up until it hits an elbow, and you actually hear the elbow go thunk. Pressure transients are the basis for most attacks on the piping infrastructure. So in this case, you have you've got a pipe. If the valve closes fast enough, then a pressure transient is going to run from the valve back and hit and reflect back off of it. So the water moving through the pipe is actually the weight actually increases exponentially with the size of the pipe. So if you have a 4-inch pipe that's running 60 feet, then you've got about 1,200 pounds of force going there. But if you have a 12-inch pipe running the same distance, you've got about 11,000 pounds of stuff running in there. If they're both running at 30 miles an hour, when it suddenly stops, that's a significant amount of force. So whether or not the shock wave forms is actually dependent on the very last closing part of the valve. So as the valve's closing, it can close really fast, and it's only when the valve actually touches the seal that the water hammer forms. And so we did a bunch of experiments with them, and so you never quite know where the water hammer, what the weakest link is going to be. In this case, the weakest link in one particular case The weakest link actually was the seals on the valve. And so in this case, we've got the valve, we close the valve really fast and we're going to try and damage the piping structure. But really what happened was the seals blew out. And they're only little holes, but at 75 PSI in a big pipe, this is basically several garden hoses worth of stuff shooting out the bottom. So in this case, what happened is we're like, okay, start the water hammer. And then like, turn off the water. And the water wouldn't turn off. It just kept spilling out the front of the pipe. So I'm going to skip that. So one of the things that you can get about water hammers is you have this big volume of water. It's moving through the pipe, and it comes to a sudden stop. That's a lot of energy. The energy there is almost always converted to heat. So if you go look to where a water hammer has actually destroyed a piping structure inside of a factory, one of the things that's almost always observed is that this water hammer is actually, the pipes are hot to the touch. So if you open the pipe and let the water slide through and you slam it and the water slams to a halt, it's going to turn most of that energy into heat. And if you open it and close it again and it slams to a halt again, you get heat again. So by cycling the valve, you can actually heat the chemicals, which is very useful in place shifting the chemical reactions from someplace to someplace else. You can actually use the water hammer effect to actually heat the liquid. So this is a gravity hammer or a steam void collapse. And so this actually happened a couple of times in a big coal plant. And so in this case, what you've got is you've got a slug of steam inside of a liquid line. And so you have a cold water at the top and hot water at the bottom. So if you can push the slug of steam through the line, what happens is it bubbles up through the top, and as soon as the steam bubble pops through, the cold water drops down and hits the steam below. And what the steam then will transition from a gas into a liquid and actually create suction and suck the top back down and slam on top of it. So if you've got several tons of water in the tank, then that's several tons of force that are sitting there popping on top of it. So you can also use check valves to start your water hammer. So a lot of times you put flow control valves. So everything's meant to pump in one direction, and you don't want it to pump back in the other direction. So the pumps kick on, pumps in the one direction, and then it comes back, and the check valve slams shut. So you can also come over there and with a pump, kick the pump on and cause a water hammer by just pushing against the check valve and let the check valve slam closed over and over again. So once you, besides water hammers, then you also have cases where pipes are meant to carry liquids. So I'll speed up a little bit. Pipes are meant to carry liquids, but interesting things happen when pipes carry liquids and gases. So if you actually have a pipe carrying the liquids and gases, and the gas is moving at a different speed than the liquid, as the gas flows over the liquid, it'll actually form little ripples in the liquid, and the ripples get bigger and bigger and bigger until they actually touch the top of the pipe. And once they touch the top of the pipe, they actually form a seal, and they take the water and they push it through the pipe really fast as all the pressure builds up behind it. And so the hard part about those are actually getting figuring out the stuff. But you can actually use this, what's called a biphase slug with piston effect. So in a biphase slug with piston effect, you actually get this effect where you get slugs running through the pipe, and then you get your unreacted chemical in the middle of it in some sort of vapor form. And if you close the valve really quick, the slug will actually push against and compress the liquid. And once the liquid is compressed, then it can drive it above its activation temperature, and you can get a chemical reaction. So the last one I'm going to cover real quick, because I only have a few more minutes, is a vacuum collapse. So we tend to build lots of things that are round because it's really efficient. And round things take lots of positive pressure. But round things tend not to take negative pressures very well. So if you look here, we have lots of instances of where negative pressure has happened. Then once you get the negative pressure, just like here, eventually you get something to buckle on the side and everything collapses down. So you can get down to negative 14 psi. So a steam collapse is a variation of a vacuum collapse where you're actually going to put something hot into the vessel, take it out of the vessel, and let it cool down. And as the as the steam transitions from a gas to a liquid, it creates a lot of force. So one cc of steam, or 1 cc of water turns into, it's like 51 liters or something like that of steam. So you get these massive pressures that you can actually sit there and crush it. So in the steam collapse, most pressure vessels are actually rated for a perfect vacuum. So if you take a big reaction vessel, you're not going to be able to collapse a big reaction vessel, because it will take a perfect vacuum. But while the vessel is stamped with a, I'm going to take a perfect vessel, then all the stuff we bolt onto it isn't really rated for that. And more often replacing steel pipe with plastic pipe because it's cheaper and better and all those things. So a lot of times you can get a vacuum within the reaction vessel and then crush the, and that holds, but then all the pipes and everything you hook onto it will actually crush. Okay, and so then the last one that I'm gonna run over real quick before we end up is three-phase attacks. And so a lot of times in industrial processes, you have three-phase attacks that are motors and pumps that are going in three-phase. And so they're sitting and going around. But if you actually bring in a motor out of phase, when you bring in the motor out of phase, then there's actually a torque to bring them both into phase. And so if you have two generators sitting next to each other and you bring them in a phase and they're the same size, they're both going to be torqued back towards each other. If you have one bigger generator and one smaller generator, that's going to experience a lot more force. And so the classic case, this is pure Newtonian mechanics. The classic case of this was the Aurora experiment done at the INL, where they bounced the generator up and down off the floor and broke it into little pieces. And electric power gets a lot of the three-phase attack love, but whenever you create the torque, that actually works on the working fluid. And so this is actually a failure right here of where a three-phase attack or three-phase incident on a pump caused a water hammer effect. And so in this case, the electric power went up and down. It brought a big pump in out of phase, and that big pump then caused a water hammer. The water hammer went down and destroyed the piping system. So by bringing in, by control of the electric power, you can actually cause transients to happen inside of your fluid systems. So, but as an attacker, you're doing all this blind. You have to go feel your way. And so this is a lot of what I spend my time looking at is how to go look at this thing. So this is a temperature graph of the barrels collapsing here. But at the end, you can see that instead of the temperature going down and we get a nice collapse at the end, you see a bump and a ripple going across there. And so this is actually what happens if you put a vacuum breaker on top of the pressure vessel. You can see the vacuum breaker kick in and stop the attack. And so one of the things that we have for the we study in physical damages, how remotely are we going to spot these types of defenses so that we can test something, move on, and go hit the next thing. So then I think I'm out of time. So then looking at this particular one, we have a bunch more attacks that we can do. If we wanted to do a vacuum collapse, we have a bunch of liquid in a tank and some pumps. Let's hook the pumps up to it and close all the valves and try to pump the tank out until it collapses. We have a whole bunch of valves. We can try to do water hammer, cycle these things really fast, get pressure transients moving around them. There's a lot more attacks that we can do that are actually kind of the bread and butter of things, and things that the engineers generally don't think of. So with that, I'm going to open up to questions, and I apologize for demo not working, but if there's any questions, I'll take them now. Okay, yes, I think we'll set this up over the ICS Village, and we'll collapse them there.